So, good morning, good afternoon, good evening to everyone. This is the second lecture of the course Representation of Compact Groups. So, in lecture one, I will start by doing a summary of what we did last time. Mainly, we introduced the basic definitions and some results, okay? So the most important definition is what is the course about. The final dimensional linear representation of a compact group is a pair B pi, where B is a finite dimensional complex vector space, and pi is a group homomorphism from the group to the invertible linear maps of V such that it is continuous. And we saw some examples of linear representations. Today we're going to see some structural results of representations. And in the last lecture, we are going to see one of the most well-known results about representations of compact groups, which is the Peter-Weyl theorem, and some explicit examples, of representations, because it depends on in every group has its own theory of representation. So today we're going to see a lot of structural results that says that more or less how one can find representations of the group. But when you pick a particular group, then to describe all the representations is sometimes it's quite hard to describe them explicitly. Okay. So for every group, the representation theory is important, and sometimes it's quite beautiful to do that. So in the last lecture, we're going to pick up one group, and I'm going to describe some representations. Okay, so suppose we are given a representation of a group. So we fix a basis of our vector space, and it's dual basis. So since for any element of the group, we have a linear map, and this linear map give us a matrix in the certain basis, and for this matrix, we can pick up an entry, and this entry give us a function from the group to the complex numbers, and this function is called a matrix coefficient, yes? And how do we compute the matrix coefficient? We just, for any fixed element of G, we let it act on an element of the basis and then evaluate on the dual basis. Yeah. So in that way, we get a continuous map from the group to C, and these are called the matrix coefficients. They're going to be important from now on. Okay. So that is the idea is for any element of the group, we get a matrix by fixing a basis. And to understand this matrix, the idea is to understand all the whole set of matrices given by elements of a group. Then, so we have an idea of the structure of the group. So that's the idea behind. So before I forget, in the first class, someone told me I wrote something like this that was wrong. So SU2 is isomorphic to SO3, and I don't recall who told me that, but it says it's a double cover. SU2 is a double cover of SO3, and actually he was right, because I was thinking in the proof, but it was wrong. Actually, what is true is that PSO2 is SO3. What is PSO2? Is the group of unitary matrices of the determinant 1 divided by the identity and minus the identity. So I forgot that. And this is actually SO3. The group of orthogonal matrices with determinant 1. So he was right. Yeah. Okay, so to fix notation, if we pick a representation, to relax the notation, we are going to write simply x dot v if we understand, or it is very clear from the context, which is the map pi, okay? So we write only x dot v. So this is the idea that the group is acting on the vector space by linear maps. Yeah. Okay, so let's start by some easy lemma. This easy lemma will give us some linear representations that any group has. For example, the first one is that any group has always the trivial representation. The trivial representation is given by a constant function such that in any element of the group is 1. This is a one-dimensional representation. And it is called the trivial one, okay? This is the trivial representation. So any group has a trivial representation. So we always have a representation. Another representation that one has is, if you give me a representation of the group, we can consider the dual representation, which is given in the dual space of the vector space. And this is denoted by PC because this is called the contragradient representation or dual. It depends on who is talking, if it call it contragradient or dual. And what is the formula? The formula for defining the representation is given by this formula, is how do we act with an element G? I don't know why I wrote G and not X. How do we act by an element G on a function F? We just act on the element V. Yes. And here I did a mistake. I forgot to write. There is a typo. There is a -1 there. Yeah, I have to write it well. And when I can pass the slides to Gisela to upload it somewhere if you want to have the slides. So I have to correct this typo. So this gives us a representation. Given a representation, we have always the contragradient representation on the dual vector space. And it's not true that it is always isomorphic to our representation, okay? So it is a new representation. So this is a way of getting one representation from another representation. Another way of getting new representation from old ones is given by the direct sum. If we have two representations, V1 and V2, then the direct sum is again a representation. And the idea is the following, which is how we describe the action. So an element X acting on an element of a direct sum, I will write the element of a direct sum as V1 plus V2, is just by acting on the summands, okay? Since the action on each one is continuous, this action is going to be continuous. Yeah. And yeah, okay, one can prove that it is a representation because in every component is a representation, okay? One can prove that one has the homomorphism of groups. This is an homomorphism of groups because each one is an homomorphism of groups. So this goes from LV to V1 plus V2. Okay? So the exercise is to prove that this is, again, a group homomorphism. This is an easy exercise. Another way of getting another representation is not to consider the direct sum, but the tensor product. So if you don't know who is the tensor product, you should know by now. If not, you have to read it before the SIMPA school starts. The tensor product is just, if you don't know who is the tensor product of two vector spaces, a very easy way to understand it is is just another vector space where the basis is given by elements of the basis with pairs of the elements of the basis, one of V1 and the other one of V2. Yeah, so by counting, it's a vector space of dimension given by the dimension of V1 times the dimension of V2. So how do we describe the representation in the case of vector spaces? Almost very similar to the representation of the direct sum. If we take an elementary tensor, what is an elementary tensor? A tensor is something like this. That is an element given written like the product of two. In general, any element of the tensor product is a linear combination of this one or a sum of this one. So we call these kind of elements elementary tensors. So the action on an elementary tensor is given by we act on the first one and we act on the second one. Just simply like that, okay? And how do we act in a sum of these elements? Just by acting on each summand, okay? We linearize this notion. So this is for every V1 in V1 and every V2 in V2. So since we are putting X on the first leg of the tensor and in the second leg of the tensor, we call this the diagonal action. Yes, the idea is we divide the X in two legs and act on each legs by this one, and it's called diagonal, yeah? So this is not a difficult proof to do. So if you're interested, I recommend you to do that because you start to understand how it works to have representations. So this lemma gives us a way of constructing new representations from some representations that we have. And the question now is, okay, can I obtain all representation of a group by doing all these operations? And the answer is, in general, yes. In the examples that we're going to see is that with all these operations, we can get all representations. And this can be described by using category theory, or more in classical terms by describing them explicitly. So in the last lecture, we're going to see how we do that for a unitary group. We're going to use tensor products and sums, yes? For only one representation, we're going to pick only one representation, which is the standard one that I introduced in the first lecture. And with this one, we can obtain all of them, yes? But we need to develop some theory to prove that actually they are all of them. Okay, now we have some definitions in order. So the first of all is we're not going to consider any representation because we only will need the representations that are the essential part of any representations. This is what we call irreducible representation. So representations that we cannot decompose. And for the other representations, we are going to prove that any representations can be decomposed into these atomic ones, into these irreducible ones. So what is a subrepresentation? First of all, a subrepresentation or an invariant subspace is a subspace of the vector space V given by the representation, such that the action of the group divided invariant. So the action of any element of the subspace is inside the subspace. So this is an invariant subspace. And what is the idea? The idea is that if we consider this subspace of V and the action of any X restricted to the action of U, this is again a representation. Okay, since it is a subspace of our vector space, we call it a subrepresentation or an invariant subspace. So we call a representation irreducible If it is not zero, so the zero representation is not considered reducible, and if it has no invariant subspaces other than 0 and V. Of course, 0 is a subspace, is an invariant subspace, and the whole V, of course, is a subrepresentation again. So it is irreducible if it has no invariant subspaces other than 0 and V. A representation is called unitary if it has an inner product such that all the elements of the group act as unitary linear maps. Yeah, what does it mean? So it means that we are acting on vector spaces. So any vector space has an inner, it is finite dimensional, it has an inner product. But the thing is, it has to have an inner product such that the action is unitary of the group for any element of a group, and explicitly it means that for any element of the group, the adjoint of the linear map is the inverse of the linear map determined by this element x. Here we have another typo. I had to write here x, not g. So if writing this using the inner product is that the action of V and W, and then the taking the inner product between these two things is the same as taking the inner product between V and W. Yes, for all x in G. So when we have this, we call the representation unitary. And the definition is that given two representations, we call a morphism of representations, or for short, intertwiner, between the representation V and W, if an intertwiner is a linear map such that the map commutes with the action of the group. In other words, it means that when we talk about linear maps, we have this relation that the action in W composed with T is the same as T composed with the action in V. Yes? So in some sense, T commutes with the action of X. Commutes means if it acts first in V and in the image acts on W, okay? And it has to work with for any X in the group. So any two representations are called equivalent or isomorphic if there is an intertwiner that is invertible. Yeah, one can prove that if one have an intertwiner which is invertible, then the inverse is also an intertwiner. Yes, this is an exercise. So in general, we call the set of intertwiners between two representations by home G. Yeah, we have sub G here, but saying that they are intertwiners, or they are, sometimes we call them G maps, or G linear. They are G linear. Yes, because the action of G commutes with the maps. And if we take V equal to W, we just write the endomorphism space. Okay? So now examples. Any one-dimensional representation of G is irreducible because there is no space to have invariant subspaces. Yeah? For example, the trivial representation is an irreducible representation. And any two one-dimensional representations are isomorphic if and only if they are equal. And how do we see that? So let's write this down. So suppose we have two one-dimensional representations. Of a compact group G, okay? And suppose that T is an intertwiner. So let's write V as the multiples of one element V because it is one dimensional, and W is the multiples of W because an element W, which is because it is one dimensional. So let's put V0, W0. So by definition, we have that T of X acting on an element V of the vector space V is exactly as X acting on T of V, yes? But T of V is T of this V is a multiple, say an A for V0, and this is linear, so this is A of TV0, and TV0 is a multiple of the other generator, so let's call it, I don't know, B of W0. Yeah. So if we write this, then here we have the action on V0 or in any V has to be a multiple again of V0 because it is one dimensional. So let's put it alpha of V0. But since it depends on the action of X, so this alpha is actually depending on X. So let's write alpha X of V0. The same with the action of W0. Let's put it beta X W0. So if we use this in this relation, then what do we got is T of alpha of X of V is equal to, this is equal to alpha of X of T of V, and this is beta of X of T of V, and this is true for any V in V, so it means that alpha of X has to be equal to beta of X for all X in G, so it means that V pi is exactly equal to W rho. Okay, so one-dimensional representations are different, or if they're isomorphic, they are equal. Yes, if they are not equal, they are non-isomorphic. So this is easy to detect if we have different non-isomorphic one-dimensional representations. For the representation of a bigger size or bigger dimension, and then we have to work more. Yeah. Okay, so there is, as I told you, we're going to play a lot with tensor products. Why? Because we can get a lot of representations by just having one representation. So given one representation, V, we can tensor it with itself, and by the lemma above, we have another representation, which is given by V tensor V. So V tensor V has two sub-representations inside. The first one is given by the elements of this form. We call it S2V. It is the span of the elements of the form B1 tensor B2 plus B2 tensor B1, such that B1 and B2 are in V. By this formula, one can prove that this is an invariant subspace. And the other one is the exterior power, and this is the span of the elements of the form B1 tensor V2 minus V2 tensor V1. So the first one are called the second symmetric power. And the second one is called the second anti-symmetric power. and they are both sub-representations. Actually, one has that more than this, is that the tensor product, the whole representation, the tensor product, can be described as the direct sum of these two spaces. So in this case, we can describe our representation V tensor V as the sum of two representations, yeah? And the idea is we are going to do that for any representation. The first thing is we are going to try to decompose our representations into smaller ones till we get irreducible representations. And the question is, can we do that for any representation? Can we decompose any representations as sum of representations of irreducible ones? And spoiler alert, yes, we can do that. The bad thing is sometimes it's difficult to find the reproducible representations appearing in one representation. Yeah, so we need more tools to find that. So another way to find representations is by looking at kernels or images of intertwiners. So if you had an intertwiner between two representations, then the kernel is a sub-representation of the domain, and the image is a sub-representation of the codomain. So this is an exercise, which is also very easy to prove, okay? So I leave a lot of exercises because we don't have much time to do everything in class. So before I continue with the next proposition, do you have any questions? Do you have any questions or remarks or comments do you want to make? Feel free to talk or to ask anything, okay? Okay, if not, yes, we have in the chat. Yes, Willie, I'm seeing this now. Yes, it is G minus one. I suppose there was in the contragradient representation. Okay, so let's continue. The first thing is that we talk about unitary representations. So the unitary representation is a representation that all the elements are when we see them as linear maps on the vector space are unitary. And the thing is, we can endow to any vector space with the inner product such that the representation is unitary. And how do we do that? So we use the Haar measure. So this is very specific for compact groups or finite groups. The finite groups are compact, that we have the Haar measure. So it's not true for things that are not compact. Yes. So how do we do that? So the proof is very classical. So I will do the proof because also it's beautiful. So what's the idea of proving this thing? So okay, we have a finite dimensional vector space. So let's pick any inner product. On V, on G, okay? On G, on V. I don't know why I wrote G. So this inner product might be or not good for our action of the group. In general, it's not that any element of the group is a unitary linear map. So since we don't know if this is true, we take like all the sum for, so I want to say, we have to take an average. So the idea is the following. So we want to make a new inner product of the elements of V such that the action of any element of the group is unitary. So what do? We take the sum of all possible actions on these two elements. So we take for any element X, we take this inner product, okay? This is a new definition. So we have to do that for all elements of the group. And since we have to do it for any element of the group, we would like to take the sum, but the sum is not quite correct because the group may be infinite. So we take our hard integral and we write something like this. So, okay, what are we doing here is we may consider this thing as a map defined by two elements, V1 and V2 of the vector space, that takes one element of the group and give us a result, a complex number. Yes? Since the action is continuous and we are dealing with finite dimensional vector spaces, this function f is actually continuous. So we are integrating a continuous function. So by definition, this is the measure of this continuous function. Yes? So we are defining a new thing depending on the hard integral of G. And the thing is the following. This thing is actually an inner product, okay? So for that, one has to prove the following is that if we take the same element, this is always bigger or equal than 0. Yes, and this is true because we have here the inner product, and for the inner product, this is true that an element is bigger or equal than 0, and if we take the integral, it's true that it's bigger or equal than 0. Yes, as someone asked me in the first lecture, yeah, we can think about the Lebesgue integral in this case. So this is true for Lebesgue integrals. And the same is true if an element, the inner product between an element is 0, then if and only if the element is 0, then if we interchange two elements, then the interchange of them is given by the conjugate. This is true because this is true for our inner product. And the last one is that this one is linear in the first coordinate. Yeah, and doing this is a straightforward calculation to prove these things. So I will leave you these things as exercise, and let us prove that actually this gives us a unitary. So the action of the group is unitary. So let's take an element X in G, and let's see that actually the action of X on the B1 and B2 and taking the inner product is the same as having B1 and B2. With this new tensor product. So let's do that. Maybe I'm not writing for X because I'm using X in the integral. Let's write Y. So, okay. So what is the new inner product of Y V1 against 1 V2? So this is the hard integral of the inner product of Y not Y, X acting on Y V1 and X acting on Y V2. Yes, but this is actually because it is a representation. This is the same as xy acting on V1, xy acting on V2. This is not the G here, yes. And if you look, we look at this carefully, this one, as I wrote before, this is the action, this is the function V1, V2, FP1, V2, but evaluated in XY, yes? So what are computing here is the measure of the function f v1, v2, but translated by y on the right. Yes, it was the definition of the left of the right translate of a map. And for that, we know that the hard measure is invariant our right and left translation. So this is again m of fp1 v2, and this is exactly v1 v2g. So here you see we're using all the properties of the hard measure. And with this, we get that any representation is difficult to say in English, is unitarizable. So it has an inner product such that the action of any element of the group is unitary. So we're going to assume from now on that all representations are unitary. So there is a question. Yes, this is a formal argument that we can change coordinates in G. Yes. If we do it for finite groups, you do it by hand. Actually, we're using the same fact that the measure is right or left invariant, but you change code, you change variables by hand, okay? And the idea is when one constructs the hard measure is doing the same trick. Yes, one had to sum over everything, and the things are compact, so we get everything is correct. So the compactness of the group is important here. Because if not, we cannot do that. Yes, we cannot play with that. So one can do representations of any group. Yes, one can, but it's more difficult. And that's the thing. But when the group is compact, then we have more tools. So and the formula that I described above is the remark. By the formula, I propose a formula for making a unitarable, to unitarize the inner product. So if our inner product was already invariant, for the action, for the G action, then the formula above gives us the same result, okay? It's the same. So this one is exactly the same. So if the inner product was already invariant, we are not changing the inner product, yes? Okay, so using this inner product, we arrive at our first important result, which is a corollary of the proof I just gave you, is that any representations is a sum of irreducible representations. Yeah. So this is important because to understand a representation of a contract group, we have to understand the irreducible ones, because any representation is a sum of irreducible ones. So how do we prove that? So I'm going to do the sketch because if not, I have not much time. So I give you the ideas. So what do we do to decompose a given representation? So we take a representation V. So if V is irreducible, okay, we don't have to do nothing because it's already reduced. So if not, V contains an irreducible representation. Yeah, it's not irreducible. It contains an irreducible representation. It contains one representation, a sub-representation, which is not zero and everything, and going like this. If it's not irreducible, then we can apply the same algorithm again, and then the sub-representation will contain another sub-representation which is not zero and everything. And if this is not irreducible, then we go down, and since the dimension is finite, then we find an irreducible representation. So like this, we find an irreducible representation, a sub-representation that we call V1, okay, of V. So now V1 orthogonal is also a sub-representation of V, okay? So when I write V orthogonal, I'm thinking about we have a unitary representation, and V orthogonal is the elements of V such that is zero with respect to the G invariant inner product. This is for all V1 in V, okay? This is also a sub-representation of V, and because it is orthogonal by linear algebra, we have that V is V1 direct sum V1 orthogonal. And this is the composition as linear vector spaces. Of course, it may not be the composition of representations, but since we are working with this inner product that is given that any element of the group is acting a unitary, so this is G invariant, this inner product, so actually this is a composition as representations. So, okay, we have a decomposition as representations. So V1 is reducible, but V1 orthogonal maybe not. So we do the same. If V1 orthogonal is reducible, then we are done. If not, we continue like this. We proceed as before and find a sub-representation. So we describe V1 orthogonal as V2 plus V2 orthogonal with V2 irreducible. And we follow like this. So at the end, we will have that V is equal to the sum of irreducible ones. Yes, this is the sketch of the proof. And everything stops because we are working with finite dimensional vector spaces. If they're not finite dimensional, then we have some issues, okay? We can work with the Zorn lemma and things like that, but we have the problems, okay? So this works for finite dimensional representations. So every finite dimensional representations is called complete irreducible. Yes, it means that we can decompose it as a sum of irreducible ones. So Willie is asking, I need to prove that I need to decompose to prove that it's completely reducible. So if we have an irreducible representation, then I have a complement. So actually not irreducible. If I have a sub-representation, I have a complement that is actually also a representation. If I can do that, then I can use the same proof. Here, from doing that I have a complement that is also a representation, I'm using the inner product, okay? And for the inner product, I need the group to be compact, or for some reasons to have
What I meant
an inner
is
product that is G invariant. If I have an inner product that is G invariant, we can do that. But
yes,
it depends on the representation. Not any represent. Not if the group is not compact, I cannot say that any representation has a G invariant inner product, or any representation is completely reducible. So we can find for a sub-representation a complement. Yeah. This is the thing. For other kind of groups, with this property we call it reductible. Yes, unitary means equipped with an inner product which is G invariant. This is what I wanted to say before. Maybe it was not clearly stated. Yes. Yes, we have an inner product that is G invariant. And this the inner product is given by the Haar measure. This is why we are using that the group is compact. For algebraic groups, they are called reductive if this kind of things happens, but we are not using the G invariant inner product. We're using another thing. It has to do with the structure of the group. And all the finite groups are on over C satisfy this property. If the field is not the complex numbers, it is not true. Okay. Any other question? So what's next is called a very nice result due to Schur. And actually it appears everywhere because it's so intuitive that it appears in everything, okay? Here we are going to state that for representations, but in general it works for any actions of anything on vector spaces or on other spaces. So the idea is very clear and it applies everywhere. So this is called the Schur's lemma. Actually for us it was going to be a proposition, but I will call it Schur, okay? This is from now up to now is the only result of Schur that we're using. So the Schur lemma says that if we take two irreducible representations and we have an intertwiner between them, so a G invariant map, a map that is G linear, then the map is zero or an isomorphism. So if the representations are irreducible, we don't have much choice. It's zero or an isomorphism. So if we take the same representation, and this intertwiner is in the endomorphism of the representation, of course they are isomorphic. And in this case, we can say more. We can say that this intertwiner is just a multiple of the identity. Yes? So the endomorphism ring of an irreducible representation is just given by the complex number. So in some books, this is the definition of irreducible representations. When we talk about category theory, so we want to describe something that say that something is reducible or simple, we say this, that the endomorphism of the objects is just the trivial representation, which is in this case the field. Yes. So again, so I'm going to do the sketch of the proof. So as exercise, left you to fill in the details. So how do we do the proof? The proof is very nice and easy and short. So let's take an intertwiner between V and W. So what I told you before is that the kernel of T is a sub-representation. And the image of T is a sub-representation of W. But the thing is, the representations are irreducible. So we have not too many options. So the thing is, okay, if V is reducible, we have two options. The kernel is zero or the kernel is everything. Yes? And here the same. The image is zero or the image is everything. Yes. So if the image is 0, then the map is 0. Okay, so nothing to say. So if the image is everything, then T is surjective. Okay. Now we go and look at the kernel. So the kernel, if the kernel is V, then T is 0, which is a contradiction because we are assuming that it's not, okay? Yeah, because it has to be surjective, and the image is reducible, so it cannot be 0. So the kernel has to be 0, so it means that T is injective, so it is an isomorphism. And that's the proof. Yes. And now, what if we take the same representation? So if T is an operator between V and V, and since we are working over the complex numbers, T has an eigenvalue. And what does say lambda? Yeah. So what does it mean to have an eigenvalue? So that the kernel of T minus lambda, the identity, is not 0. Okay. But what do we know is that T is an intertwiner, and any multiple of the identity is also an intertwiner. So T minus lambda, the identity, is also an intertwiner. So, okay, it is an intertwiner between V and V is irreducible. So, but what we did before, this is 0 or an isomorphism. But it is not an isomorphism because we know that the kernel is not 0, so it has to be 0. So what we did before, we said we know that this one is the 0 map, so it means that T is lambda times the identity. And this is the proof. Okay. So a consequence of the Schur lemma is that if we have an abelian group, then any reducible representations are all one-dimensional. And why? Is because, how do you say it shortly? Because I'm running out of time. So if you take, if V is an irreducible representation, and if the group is abelian, we know that xy is equal to yx for all x and y in G. Okay, this is the thing that is abelian. So if this is abelian, it means that the action of any element y, which give us a linear map between V and V, is just a linear map. But in the case that G is abelian, it is an intertwiner. Yes, because the group is abelian. Yeah, because to be an intertwiner means that it has to commute with the action of any x, but this is exactly by the definition of the action. This is this one, and this is equal to this one, which is equal to this thing. Okay, so it commutes with the action for any x. So the action of any y as an intertwiner. So it means that we have an intertwiner between V and V, which is reducible. And what we saw before, it means that the action is just a multiple of the identity. This linear map is a multiple of the identity, so this is true for any y. So we put it lambda y of the identity. And so it means that the action the representation is given just by this scalar. So it is one-dimensional because it is irreducible. Yes. We take only one vector since the action is given by a scalar. The vector subspace spanned by one vector is a sub-representation. So since the representation is irreducible, it has to be everything. So, and this proves that if the group is abelian, only the one-dimensional representations are the reducible ones. So, okay, let's take the circular group. If we take the circular group, the finite dimensional representations are given by, parameterized by the integer numbers. So the representations, let's put them Pn of the circular group to, this is Gn of C, these are one-dimensional things. It's just taken by, we take any set in the circular group and the representation is making the power of n. Yeah. The easy things to prove is that this map give us a representation, a one-dimensional representation, and it is one-dimensional, then it is reducible. And if we pick different ends, then we get different one-dimensional representations. And I show you that if the one-dimensional representations are different, then they are non-isomorphic. So in this way, we get infinitely many one-dimensional representations which are irreducible for the circular group. The difficult thing to prove is that all one-dimensional representations are like this. So this is an exercise. It's not so difficult, but it has a lot of details. Yes? So we have to prove that any map from the circular group to C star to the invertible elements in C is given by a power. So this is one has to prove this thing. So you see, just for the easiest group, a compact group, the circular group, we have infinitely many non-isomorphic irreducible representations, which are one-dimensional. So if the group is non-abelian, then we have more things that are not one-dimensional. Yes, I'm going to see that in the last lecture, an example of how to produce a lot of representations which are not one-dimensional. So a couple of remarks before ending is that for any pair of vectors, we can define the following maps that we're going to put the name for these ones. That given, since we have an inner product which is G invariant, because we are thinking that the representation is unitary, given two vectors, we can produce from G to the complex numbers. It's just we take any element of the group, we let it act on a vector, and we make the inner product with the other element. So it gives us a complex number, and it gives us a continuous function. And actually, one can prove that this is, well, okay, it's a continuous function from G to C. Yes? So these functions are in the set of continuous function of G. And we call them also matrix elements, matrix coefficients, because in some sense, given U and V, we can extend taking U to a basis of the dual by using the inner product, and taking V to a basis of the vector space V. Okay, so this is why we call them also matrix coefficients. So using again the Haar measure, we can define also, as usual, an inner product on the space of continuous functions. Thus, we do as usual. We take the integral and we just multiply f of x times the conjugate of g of x. This gives us an inner product. And having an inner product given by an integral, we can define the space of LP functions, which are the integral, the functions that which this integral is finite. Yes. So if you take P, so also we have a P norm given by this formula, as usual. And in the case P is 2, we have a Hilbert space. Yes. So what are we going to do next? In the next class, we're going to try to understand this space. This is a Hilbert space of functions of L2 functions over G. And the Peter-Weyl theorem will give us a basis of this, an orthonormal basis for this L2G. The thing is, this orthonormal basis is given by the matrix coefficients that I introduced you before. Yes, this is the beautiful Peter-Weyl theorem. I hope to get it very fast so we can do some examples over the unitary group. Yeah. So this is all for today. Are there any questions or remarks that you want to make? So Gisela, you can stop the recording if you want. No. No, that's right. The LP functions are not necessarily are not continuous. Yes. The thing is, we can define, the set of LP functions using the Haar measure. Yes.